Welcome to the presentation on distillation, focusing on its basic principles and methodology. Presented by Dr. S.K. Singh, this session will guide you through the fascinating world of simple distillation. Distillation is a sophisticated separation technique that utilizes differences in boiling points to purify liquids or separate components of a mixture. This process involves converting liquids to vapor through heating, followed by condensation back to liquid form. Widely used in both laboratory and industrial settings, distillation is a key method for purifying volatile compounds. The core principle of distillation revolves around unique boiling points. Each liquid substance has a specific temperature at which it transitions from liquid to gas, allowing for selective evaporation based on volatility. This differential in boiling points forms the foundation for separating components in a mixture, enabling the collection of purified substances. Simple distillation involves a single vaporization condensation cycle, effective when components of boiling points differing by at least 25 degrees Celsius. Fractional distillation uses a fractionating column for multiple cycles, suitable for closer boiling points. Vacuum distillation operates under reduced pressure, ideal for heat-sensitive compounds or substances with very high boiling points. The physical process of distillation begins with heating the mixture, increasing molecular motion and overcoming intermolecular forces. As the temperature approaches the boiling point, vapor formation occurs, followed by cooling and condensation. The condensed liquid is collected as distillate, while the original mixture becomes richer in higher boiling components. Vapor pressure plays a crucial role in distillation, with lower boiling point components having higher vapor pressures. Monitoring head temperature is essential to ensure accurate measurement, and determine when to change collection vessels, aiding in the efficiency of the separation process. Simple distillation faces limitations such as boiling point proximity, incomplete separation, azeotropic mixtures, and vapor-liquid equilibrium. These factors can hinder the ability to achieve pure components, requiring careful consideration during the distillation process. The main components of distillation apparatus include the distillation flask, heat source, condenser, and receiving flask. Each plays a vital role in the process, from heating the mixture to condensing vapors and collecting the purified distillate. Setting up the apparatus involves assembling glassware, placing the thermometer, connecting water outlets, and ensuring proper sealing. These steps are crucial for preventing vapor escape and ensuring accurate readings during the distillation process. Heating the mixture requires controlled techniques to prevent violent boiling and ensure steady vapor production. Gradual application of heat and the use of boiling stones or chips can aid in achieving precise distillation, balancing efficiency and separation quality. The collection and separation phase involves reaching the boiling point, stabilizing temperature, and collecting distillate. As the temperature rises, the most volatile component vaporizes first, flowing into the receiver, allowing for effective separation of components. Monitoring temperature at the distillation head provides crucial information about the distillation process. Completion is indicated by the absence of liquid distillate, significant temperature rise, and the presence of non-volatile residue, ensuring the process is efficiently tracked and completed. A labeled diagram of the distillation setup highlights the key components: distillation flask, condenser, thermometer, and receiving flask. Understanding their roles is essential for grasping the distillation process and ensuring successful operation. Distillation elegantly separates dissolved salts from water, a process filtration cannot achieve. This principle is vital for desalination plants, converting seawater into drinkable water, addressing water scarcity in coastal regions. The separation of alcohol and water through distillation involves heating the mixture, condensing vapors, and collecting the final product. This process enriches the ethanol content, demonstrating the effectiveness of distillation in separating components based on boiling points. Safety precautions in distillation include fire hazard prevention, personal protection, pressure concerns, and chemical handling. Ensuring proper ventilation, wearing appropriate safety gear, and checking for blockages are essential for safe operation. Distillation has diverse applications, from water purification and spirits production to petroleum refining and essential oils extraction. Each application utilizes distillation's ability to separate components based on boiling points, showcasing its versatility. Simple distillation offers advantages such as accessibility, operational simplicity, energy efficiency, time effectiveness, visual monitoring, and broad applicability. These benefits make it a preferred method for many common separation problems. Despite its advantages, simple distillation faces challenges like close boiling points, azeotropic mixtures, heat-sensitive compounds, scaling difficulties, and purity limitations. Addressing these challenges is crucial for optimizing the distillation process. Key distillation terminology includes distillate, residue, theoretical plate, reflux, and azeotrope. Understanding these terms is essential for grasping the distillation process and its nuances, aiding in effective separation and purification. Distillation and filtration are two methods used to separate components in mixtures. Distillation works by exploiting differences in boiling points, making it ideal for separating dissolved solids or liquids. Filtration, on the other hand, uses a physical barrier to separate insoluble solids from liquids. While distillation requires heat and is moderately complex, filtration is simpler and often requires less energy. Distillation is a crucial process in various industries. In petroleum refining, it separates crude oil into fractions based on boiling points. Industrial alcohol production uses distillation to produce high-purity alcohols. In chemical purification, distillation is used to separate gases and other components, ensuring high-quality end products. Understanding the fundamental principle of distillation is key. It involves differences in boiling points to separate components. Proper equipment setup is essential for efficient separation. Distillation is widely used for purifying solvents and water mixtures. However, it has limitations, especially when components have similar boiling points. Let's test your understanding of distillation basics. Consider what physical property allows distillation to separate mixtures, and think about safer heating methods for flammable solutions. Reflect on what is collected during distillation and the limitations of simple distillation. Here are the answers to the quiz. Distillation relies on different boiling points to separate components. A water bath is a safer heating method. The distillate is the purified liquid collected. Salt dissolves in water, and similar boiling points can limit distillation effectiveness. Thank you for joining this presentation on distillation. We explored how distillation separates mixtures, the equipment used, and its real-world applications. If you have any questions or need further clarification, feel free to reach out. Your engagement is appreciated.